boundary value problems. So they'll have to be second order. That means that there's a second derivative, and there'll have to be two what are called boundary conditions. So you'll be interested in the value here between x0 and x1. So x0, x1, x, y, you're only interested in the solution between these 2 points, and these 2 points are given as the boundary conditions. Okay, so with a second order system, 2 bits of information required. First, reduce it to two initial value problems. So as usual, you let v be the first derivative, and then you have a differential equation for v. Well, for y is the easy one, dy dx equal to v with the initial value. And then you rewrite this thing. So this should be okay for you. So I'm going to just do it up the top. So if you let v be the first derivative, what are we talking here? We're talking a of x. Now, the second derivative of y is the derivative of dy dx, but dy dx is equal to v, so the second derivative of y is dv dx plus b of x. Now, dy dx is equal to v plus c of x times what? Now, a of x, b of x, and c of x are actually known functions, is equal to phi of x. And what you want to do for the dv dx differential equation is solve this, for the v differential equation is solve this for dv dx. So you take away the bxv, take away the cxy, and divide both sides by a of x. So you write it as two first order initial value problems. But the story here is you have no idea what the initial v is, the initial value of the derivative. Okay, so if this is a shooting method, so if the problem is linear, now linear basically means just what I wrote here. I think the fancy word for linear, if we want to explain everything, I think a differential equation is linear if y1 of x is a solution and y2 of x is a solution, that a constant times the first solution plus a constant times the second solution is another solution. I think that's what linear means. Now looking at that equation, that doesn't work. So it means something like that, right? Not exactly that, but something like that. Yeah, we'll leave it there. Well, anyway, when I give you one, it'll be linear as such. So what you do is, do you remember, if we go back to the, think about the pendulum again. So remember the one where you let go of the pendulum from rest and you found that, in fact, after 0.2 seconds, the pendulum went to 0. So that's called taking a shot. And then what you could do is you could increase the initial velocity to something, well, the angular velocity, and let go and see where you get. Now, it turns out if you have a linear, so for example, the pendulum equation is an example of something that's nonlinear. So what I'm describing wouldn't work for the pendulum equation. But you can average out the two shots in a certain way to figure out what the initial velocity should be. So at the moment, all we're thinking about is you're just chancing your arm, okay? So we're going to guess an initial slope. This is essentially initial slope. So that's like, okay, let's try with the pendulum release from rest. And we're going to shoot for what we're trying to hit, and we're going to get an approximation, which we call y. So then we take another guess of the initial slope. And we get another, now we're trying to get y1, but we get yb. And it turns out that there's a relationship between these. So this is called a shot 1. It's called the shooting method, shot 2. And there's a relationship between all these that we can kind of explain. Okay, so let's explain this. So let's get some data or some stuff written down. So first of all, let's get the initial point. x1, y1. And we're trying to hit, say, x2, y2. So what we do is we pick an initial slope, which we call VA. Now I just want to look at this. We're going to make VA to be the smaller one. So say a good shout is to maybe just shoot straight at it first. Okay, now it's easy enough for you to find what does it mean to shoot straight at it, because it'll just be rise over run, y2 minus y1 over x2 minus x1. And suppose that if you start with that initial slope, suppose you get this point here. So this will be x2 y8. So that's your first shot, and it's an undershot. So now what we're going to do is we're going to increase the slope. So here we'll go back to that one in a minute. Now we're going to increase the slope to this. So we're going to try VB. And suppose that this gives you an overshot. Okay, so this will be x2 yb. So let's write something here. Now one of the things, this makes most sense if you have an undershot and an overshot, but we're going to end up with a formula and it works either way. Okay, so it turns out that there's a relationship between all these. So imagine, for example, the point we're trying to get is exactly in the middle. Then if we take the average of these two slopes, it'll hit it exactly. Now it takes a bit of mathematical work to show that, but you can exploit the linearity of the differential equation to show this. So instead what it is so I'm going to just call this this distance here the difference between these two. Okay, so this is going to be, we'll say, a change in y. Okay, now the difference between the slopes is a bit harder to see on the picture because, look, I'm just going to call it delta V, the difference between the slopes. Okay, and the formula, which, remember, you don't have to learn it off or anything, but so the correct slope that will hit it is the bottom slope, okay, plus a certain proportion. Now what this proportion is, let's call this, let's write P for proportion, right, of the difference in the slopes. So the question is, what is the proportion? And the proportion is the same thing as the ratio, how much of this out of this. So if y2 is halfway up, P will be a half. If y2 is a third of the way up, P will be a third. So let's write this down. So VA, the proportion is, so y2 minus YA so that's the, yeah, out of the total, which is YB minus YA. And then the difference in slopes is VB minus VA. And it turns out that that will be exactly the slope that you need to hit this bang on the money. Boom. So you can take two shots and kind of average them out. So we can write down this formula down the bottom. We might see slightly different formulas where just like if you swap the A and the B, you get the same thing. So let's write down this formula here. Hopefully I can fit it in. So the proper slope is the first slope, which doesn't have to be an undershot. This formula still works if VA is an overshot and VB is an undershot, or if they're both overshots or if they're both undershots, it still works. And interestingly, if it hits it exactly, say with YA, then it'll be interesting what happens. So if VA hits it exactly, well then the proportion will be 0 and you just have VA. If VB hits it exactly, what will happen then? So VB, this thing will be equal to 1 and you'll have VA plus VB minus VA, which gives you VB. So it is the correct thing. So we get plus Y2 minus YA. Hopefully I can fit this in here. Will it let me? YB. Sorry now. Made a bit of a mess of it. VB minus VA. And it looks just the formula. You don't have to. to me, it's nice to understand it, and I might ask you to, like an assessment, put this formula in words. Okay, so is that the same formula? Basically, it is. The only thing I've changed is so y1 is the same thing as y of x1. Okay, so we're going to do, I think, 2 examples. Right, so example 1 here, consider a rod of length 6 meters, uninsulated along its length but in steady state. So it's an equilibrium temperature. We'll hear more about that kind of thing later on. Suppose the air temperature is 20, the heat transfer coefficient is 0.02, and the boundary conditions are at 0, the temperature is 10, and at 6, temperature is 70. So temperature is the solution of this. Using a step size of h equal to 2, which obviously is big, but on VBA you can make it smaller. Use the Euler shooting point method to approximate t of x. Okay, so first of all, we'll just do a little sketch to kind of understand what's going on. So here's one of the boundaries. Here's the other boundary. We have a thin rod. Now the bit about the thin rod is, we'll probably see stuff about that later on. And we have 3 pieces of information really. The temperature here is 10. Now I'm just going to write, what will I write? T is 0 equal to 10. That means 0 along the beam, the temperature is 10. And here 6 meters along the beam, temperature is 70. And the air temperature is 20. And this length is 6 meters. So that's what we're looking at here. So what's definitely going to be the case is at 0 the temperature is going to be 10, at 6 temperature is 70, and in between, well, we'll see what happens. But because the air temperature is 20, it's going to be a bit lower. But like if there isn't much heat transfer between the rod and the air, well, what's going to happen? Okay, so first of all, right, there's 2 initial value problems. So the first thing you're going to do is, as usual now, let v be the first derivative. And I think I'm even going to, so I'm going to write let v be the first derivative, the derivative of temperature with respect to distance. So therefore, the first derivative of v, so take v is equal to dt dx and differentiate both sides with respect to x, you get that this is the second derivative of temperature with respect to distance. And then just look at the equation above, and like what is the second derivative equal to here? Take away 0.02 20 minus t from both sides. So we're going to have an equation for t is the easy one, and then for v. So the temperature for t says, more space, the derivative of temperature is v. So I think that might be some kind of temperature gradient. And we know the initial value of t is 10. And then dv dx, we just found, is minus 0.02 20 minus t. Now we do not know the initial value of this, so this is unknown. And we're just going to take a guess. Right, so we're going to take a shot here with this slope. Now where is this slope coming from? Now if I draw another picture of temperature versus distance, I have at x equal to 0, I have temperature equal to 10, and x equal to 6, I have temperature equal to 70. Now look at the rise over the run. So that's 60 over 6. If I shoot straight at it, I get, where am I going with this? I get a slope of 60 over 6, which is 10. So the v is the slope, so we're going to try VA equal to 10. So now we're going with a step size of 2, so hopefully we have the space here. I'll just look at what's happening on the next page. Yeah, I'm going to have to make the writing quite small here. Right, here we go. So using this, so let's see. So first of all, we're going to see what's happening at 2. So T1 is, remember Euler's method, is the previous t value, which is 10, plus step size, which is 2, which is very big, times the previous slope. Now the derivative of t, we can see it there as v, and the previous v, well, we're just going to guess that it's 10. And that comes out to be 30. Okay. And actually we seem to have loads of space maybe. well, I'll just play it safe. The slope at the next point, v1, is the previous slope, which we're guessing to be 10, plus the step size is 2 times the previous derivative of v. So the derivative of v there is minus 0.02, 20 minus the previous temperature. Now you don't use 30, use the previous temperature, which is 10. And I'm assuming at this stage we know Euler's method quite well. So let's do this. 10 plus 2 minus 0.02 times 10. And I get 9.6. Okay, so we go to the next point, T2, and we'll probably put a table at the bottom to explain all this. So is the previous temperature, which is 30, plus the step size, which is 2, times the previous slope. Now the slope is v, the previous slope is 9.6, and I think that'll give you 49.2. Okay, and then the next v is equal to previous slope, which is 9.6, plus h, which is 2, times previous slope 0.02, 20 minus previous temperature, which is 30. So what will that give us? 9.6 plus 2 times minus 0.02 times minus 10. And I'm getting out 10 here. Kind of weird, but there you go. And then T3 is equal to previous temperature, which is 49.2, plus step size, which is 2, times previous slope, which is 10, equal to, that'll give us, I think, 69.2. That isn't far off. Okay. Now, I don't think there's any point calculating the next v value, okay, at this point. So we'll put what we have in the table. So sorry about that. So we got x, t. Now this is ti, so these are Euler methods. I don't think we really need the v's here, but I will put in t of x, which is exact. Okay, so you had x equal to 0, 2, 4, and 6. Now what we know in terms of the exact solution is this is supposed to equal 10, and this is supposed to equal 70. Now look what we have. We've got, well, there was no problem there. That's 10. Our T1 is 30. Then we're looking at 49.2, and then we're looking at 69.2. We're actually not that too far away. It's an undershot. Now you could try something like, oh, I'll just try 11, and then I'll try 10.5 or whatever. You could keep going like that. And that's kind of probably how Goldseek would think about this. But we just have to, because of the nature of the differential equation, we just have to take one more shot. So we need a bigger slope. Now you can do whatever you want, and you don't have to get an overshot. So you could just try 11. I think maybe 15 or 12 or 20 are all better choices. Let's see what happens on the next page. So this is an undershot, so we're going to try with 15 now. So same kind of notation. So T1, so we're going back to the start. We're going back to x equal to 0, t equal to 10, and v equal to 15, and the same differential equations. So the next temperature here, so this will be at, so maybe let's just slow down here, and just in case people are a little bit lost. So what's T1? T1 is an approximation of the true temperature 2. So that 30 is an approximation to that. What's T2? It's an approximation to the true temperature at x equal to 4. So that's what that 30 and that 49.2 represent. Okay, so let's come up here again. So T1 is previous temperature, which is 10, plus the step size, which is 2, times the previous slope. Now we're just chancing our arm with 15. So this will give us 40. Now the next slope is equal to the previous slope. So now we're going back to the start, we're chancing 15, plus step size is 2, and then the derivative is minus 0.02. Is it 20 or t minus 20? 20 minus t. Did I do that the whole way down? 20 minus t. 20 minus t, yeah, 20 minus t. Okay. Times 20 minus t, and it should be the previous t, which is 10. So this is equal to, bang it into the calculator, 15 plus 2 times minus 0.02 times 10. So I'm getting 14.6. So check, I get 9.6 over here. Yeah, okay, that's consistent. Now we go again. T2 is equal to the previous temperature, which is 40, plus the step size, which is 2, times the previous slope, and the slope of t is v, so that's 14.6. And we won't be here, I'll just put that into the calculator. 40 plus 2 by 14.6, and I get 69.2. So this is going to be an overshot. So V2 then is equal to the previous V, which is 14.6, plus step size, which is 2, times previous slope minus 0.02. Previous temperature, it's T minus 10, no, it's 20 minus T, excuse me. 20 minus T should be the previous T, which is 40. So this is 14.6 plus 2 times minus 0.02 times, looks like minus 20. And that goes to 15.4. And then we just have to calculate one more. T3, previous temperature 69.2. Now we're trying to hit 70, so this is a big overshot. 2 times, the derivative of T is V, that's 15.4. So let's bang this into the calculator, 69.2 plus 2 by 15.4, and it's coming out as exactly 100. So if I could draw a little picture here, which I suppose I can. We're starting at, why do I keep picking this stupid color? Say temperature equal to 10, and now we're trying to hit 70. Now in our first shot, now obviously I'm going to exaggerate this, 69.2, and our second shot we hit 100, which is a big overshot. The first slope was 10, the second slope was 15, so this is VB equal to 15, VA is equal to 10. Now we're going to average out these two slopes, but they're going to be very, very, now it's going to be much closer to 10 because the 69.2 is much closer. Now if you want to go back and use the formula, be my guest, in that formula, this would be the YA, this would be the YB, and this would be the Y of X1. But personally, I don't really want to use the formula because I feel I understand what the method is, which is better. So average them out. The proper slope to use is VA, which is 10, plus some proportion, which is just a little bit of the way from 69.2 to 100. In particular, it's 70 minus 69.2. So that proportion of 100 to minus 69.2 of the difference between 15 and 10, which I can write as 15 minus 10, but really should just be 5. So this, let's see what it gives us. Now, how many significant figures is probably important? We'll probably use 5. So I'm getting out 10.130. Now I get 129, but it's 1298, so that should round up. So 10.130. Okay, so now we're going to estimate again. Now we know the temperature at 0, we know the temperature at 6, we know this is going to work. Now of course you can check your answer, and maybe we'll do that. So we go again. So T2 is approximately T1, which is the previous temperature, which is 10, plus the step size, which is 2, times the previous slope, 10.13. So we get 10 plus 2 by 10.13, and I get 30.26. And the next V1 is equal to previous slope 10.13 plus step size is 2, and derivative is minus 0.02, 20 minus t, 20 minus 10. So didn't leave myself much space there. So this is 10.13 plus 2 times minus 0.02 times 10. And I get 9.73. Now I've only actually one more thing to calculate, but then we'll check our answer by going in a different color. So T2 then is the previous temperature, 30.26, plus the step size is 2 times the previous. So the previous V, because V is the derivative temperature, the previous V is 9.73. And what do we get? 30.26 plus 2 by... Now we have to understand here the step size is humongous, so the error is going to be horrendous as well. 49.72. And we don't have to calculate the next V or the next T because we know the next temperature is the temperature at 6. It's going to be 70. Now we did rounding error when we calculated this has epsilon rounding error. So we'll keep on going, but you'll note that we don't get exactly 70. So let's see how far off we are. So V2 is the previous V, which is 9.73, plus twice the derivative of V, which is 0.02, 20 minus the previous temperature, which is 30.26. That comes out to, now we're only going to use 5 significant figures, so there's extra rounding error here. So 20 minus 30.26, 10.14. And then, so this should be quite close to 60. So previous temperature is 49.72, plus step size is 2 times previous slope, 10.14. It actually is going to hit it on the nose, I can see, because of it's going to be, maybe you see it as well. Maybe now that is a bit of a fluke, because I think normally the rounding error should affect it a bit more, but happy days. Okay, so what have we actually got here? So we've got now some of the pictures. This picture, I think we should reproduce it down below a bit more accurately, and I will do that. We'll put in the exact solutions now. So we'll do what color? So we'll do really. Sure, we can make up our new color, can't we? Yeah. So let's take some points. Now I will have to exaggerate this. So just to recap, so we had the point 0, 10, which is 100% on the curve. The point 6, 70, which is 100% on the curve. We took a straight shot at it. Now so I'll have it going straight at it. Right, that was our first shot. That was V10. Now it undershot, but we'll exaggerate. So this was the point 60, and we got 69.2. Then we had an overshot. Let's go right it over. So this, and yeah, and so this went over a good bit. So this was 6, it actually hit 100, didn't it? So this was with 15, VB is equal to 15, and the other one was VA equal to 10. And then we averaged those out using the formula up here, and we found a 10.13. Now that obviously is just a little bit bigger than this. Go ahead. And it hits it exactly. Okay. Now we should put in some additional points here. So we can take this out. Let me do this. So this one uses V0 equal to 10.13. And where are the other points? So we calculated some other temperatures. Temperature 4, temperature 2. So we estimate temperature 2 is 30.26. And temperature 4, it was 49.72. Now we have to understand that step size is humongous. So there's possibly very large errors in the 30.26 and the 49.72. Just because we hit 70 doesn't really mean that much, okay? Yeah. So that's what we're doing. I think we're going to do one more example. Yeah, we'll just quickly, I think. So here's another example. Consider a simply supported beam of length 6 meters subject to this loading. Therefore, the bending moment is given a solution of the boundary value problem. So first of all, you write as 2 initial value problems. Now, the nice thing here is with the first derivative here actually does mean something. So if you let V be dm dx, this is the shear force. And I think we're pretty much straight away there, because if I write an equation for m dm dx is equal to v together with the initial value of m, which is 0, and then look at this shear force thing, differentiate both sides. The derivative of v with respect to x is the second derivative of m with respect to x, which is given here. So I get dv dx is equal to, now I'm going to write it in with the exponential now, e to the minus x minus 3 squared, which of course is the same thing. So that's the differential equation for the shear force, but we've no idea what the initial shear force is. So starting with v of 0 equals 0, now that's shooting straight across. So if I just do a little plot, again, sorry, I'm always picking the stupid color. So x equal to 0, bending moment equal to 0, x equal to 6, bending moment equal to 0. So the obvious thing is just to shoot straight across. VA equal to 0. So starting with, this really should be V of A. And implementing Hein's method. So you don't have to do it with Euler, you can do Hein's method or Runge-Kutta or anything else. The step size of 0.1. This is obviously in VBA. It ends up being an undershot. 6. I'm just going to write two significant figures, minus 53. Then using VB to be 10, we get an overshot. So let's say 6.8. That's an overshot. Using the formula, so it should be the initial slope 0 plus a proportion of the difference between them. And that's what the formula is doing. 8.826 is the correct slope to use. Actually, I could probably improve this a little bit. So this one is VA equal to 0, and this one is VB equal to 10, and we average them out. It turns out that kind of 8.9 does the money. Yeah. If you run it again, you get a tiny error at the end, and you get this bending moment equation. Often the bending moment will be plotted upside down. But yeah, that's, and look, the important thing here is we're interested in what's happening at the boundary. So again, being fancy, the region we're interested in is 0, 6, and the boundary of the region is the 0.0 and the 0.6. And here, the shear force is of interest, and you can see it's equal to 0 where the bending moment is a maximum. Yeah, okay, very good.